Okay, so in today's class, basically we will see the different diffusion reactors. What a different type of reactors are there, and for that reactors, what type of used, and basically in case of diffusion, what we are going to do is we are going to uh, deposit the dopant atoms on the silicon, either it is p-type or n-type. If it is a p-type substrate is there, on that we want to fabricate an n-type channel. So n-type doping of source and drain we need to perform. So that doping is basically done by diffusion. Okay, so in that diffusion, this diffusion process is basically having different type of reactors. So based on the type of dopant, we have different type of. So this is suppose we are going to fabricate a uh, MOSFET. This is a p-type substrate is there, and we have done the oxidation, and then we have we have deposited the silicon dioxide after the oxidation. So this is silicon dioxide and this is metal. Okay, so suppose this is SiO2. So on that, now we want to deposit N plus region or N type region for source and drain terminals, source and drain regions. Okay, so this type of deposition of N type of uh, donor donor that can generate N type of semiconductor. That dopings will be done with the process called diffusion. Okay, so diffusion is the process we will be using. So here in that diffusion process, this diffusion can be of different type. Basically, we are introducing the impurity. So to dope a particular region for a type, we are going to introduce the impurity. Okay. So based on the impurity, so either this impurity is what type. Based on that impurity, we can say whether it is a p-type doping or n-type doping. Okay. So for different n and p-type doping, the typical impurities for silicon related processing. So here typical impurities we will see for silicon. So for silicon, what is the typical impurities we will see. So if we want to dope for n-type, if we want to do for an n-type, the different impurities that we need to add to the silicon is like arsenic. We can add arsenic, or we can add phosphorus, or we can add antimony. So these are the different commonly used impurities or dopant that we need to introduce inside the silicon crystal. Okay, so that we can get an n type of dopant. Okay, similarly, if we want to go for p type of doping, then we will be going with boron, indium, even the gallium and aluminum. Okay, and for that, the most frequently used p-type dopant is considered as the boron. So boron is, you can say, the most frequently used p-type dopant. So in this part, basically we will see what type of different reactors. Okay, through which the of these dopants takes place on the silicon surface, and also we will see different and their behavior. Their behavior in this, if we want to dope silicon crystal with the boron type of dopant, then what are the different sources of this boron dopant? We will see that. Okay, so in terms of diffusion reactors, there are basically three different type of diffusion reactors are there. So based on the type of diffusant, or based on the type of dopant, if the dopant source of dopant is a liquid, or solid, or a gas, so based on that we will be dealing with the type of reactor. Okay, so if it is a, solid type of dopant source, then solid type of dopant source will be processed by a separate type of reactor. So that reactor is considered as the solid source reactor, or we, based on the type of source or source of dopant, there are different type of reactors are there basically. Okay, so here in case of diffusion, this diffusion process is done at basically at high temperature. Okay, so basically it is done with the help of heat treatment. So in the semiconductor, we will be heating the semiconductor along with the impurities available. Okay, so along with the impurities, we will be heating the semiconductor surface, and then whatever dopant atoms are there inside through this impurity, that will be uh, going to the silicon surface, and it will be deposited on the silicon surface. So this is how the diffusion. Okay, so in that, basically this in this process, uh, here the impurity should be deposited such that the depth of deposition, the concentration of dopant should be controlled, or should be uh, desired according to our requirement. Okay, so whenever we are going to deposit the dopant atom on the silicon surface, it should be a controlled process. Okay, so in diffusion, based on different reactors, we can have the different controlling factors, so that we can control the depth and the concentration of the dopant. Okay, so final goal, that is end goal, that we want is basically the uniformity. Okay, so our deposition of be uniform across all the surfaces. Okay, so that means if the complete semiconductor substrate is there, so in that silicon surface, the deposition of the dopant should be. Okay. The next one is the consistency. That means whatever deposition is going to take place should be having similar structure, similar type of deposition, similar depth should be there. Okay, from the front side. Okay, so either we are depositing from the front side or rear side, the deposition should be similar. Okay, so there should be a consistent from both the sides, and also the compatibility. So in terms of compatibility, it says like, if first time we are going to deposit the dopant. Okay, so deposition one is going to take place, and then for some time duration, and then deposition 2 is going to take place, and then deposition 3 is going to take place. Or we can suppose this is done for T1, and this is for T2, and this is for T3 time. And if we are going to do the deposition for T1 plus T2 plus T3 times at the same time, so it is done in different steps. For one time duration, the diffusion is taken. For second duration, time duration. So these are three different time duration, three different diffusion steps have been taken. if three different steps for diffusion is being done, and another system is there on which we are going to deposit, so that we are going a continuous deposition for T1 plus T2 plus T3 times at the same time. That means the complete time duration is same throughout these two processes, but here the deposition is done at a time, and here deposition is done at three different time. Then also the type of diffusion or the quality of diffusion that we have obtained should be same in both the cases. That means there should be a compatibility on run from run. So if one run of a deposition has been taken place, for the second run, if two runs have been completed, then both should be so just so so these are uh, of our the goal that we are going to achieve by using this process in uniformly. So now we will see the different types of reactors. This is the first case. This is a case where the solid source of dopant is there. If source of dopant is there, then this type of reactor is used for the process of diffusion. Okay, so here in the will be there. Okay, so this furnace will be made up of quartz. We call it quartz diffusion tube furnace. Inside that we will be this uh, slice of substrate, and there is this is the source, means the source of dopant is the source board. Source board means called as, so it's source board. Okay, so this on which we the source should dopant is a solid type, then the solid here this will be flown. So carrier gases will be flown to this, it will be controlled by this valve. Okay, so what will be the flow of the gases that we can control from these two valves, and these gases will be flowing, and these furnace heated at around 1150 degrees centigrade based on the type. So based on the type of dopant, so based on the type of dopant, different temperatures are required. Okay. So this process is going to take place at a higher temperature, more than 1000 temperature. Okay. So based on the dopant, it will be varying. Okay. So this is in case of boron. If boron is the dopant, in that case 1150 is considered the diffusion temperature. Okay. Temperature, this solid source is there, and that will be heated, and the surface will also be heated. And when this gas is flown, this gas will be passing through this uh, source, solid source that is heated, and this once the gases is going to pass through this, the source atom or the dopant atoms are going to associate with the carrier gases, and it will be passing to the slice of the carrier, or we call it the substrate that on which we are going to deposit the dopant, the silicon surface. Okay, so this will be deposited here. Okay, so this is the basic process how the deposition is going to take place. If we want to stop the diffusion, okay, so if we want to stop the diffusion, what we will do is we will remove, we will move this source board to a lower temperature. So this is the region of lower temperature. Here at the place, the slice of the semiconductor silicon semiconductor is placed, that will be at a high temperature. Okay, so that will be at 1150 degrees centigrade temperature. Okay, if we are moving this source board away from the higher temperature, then it will result in shutting down the diffusion process. Okay, so it will stop the diffusion process if we are moving the uh, source board to a colder temperature, or we call it the temperature lower than the temperature of this source, this slice. Okay, so this is how we can control. So this is the basic, the first type, that is solid type of reactor. If the solid source is there, this type of reactor will be used. Similarly, the next one is the type of reactor, that is when the dopant type is layer, the liquid source is there. Then for liquid source, this is the setup of the diffusion reactors basically. So here, instead of placing the solid, we will be placing the dopant in the form of liquid, and this gases, the carrier gases, will be made to flow through the liquid uh, dopant. So this liquid dopant will be supplied the gaseous, this carrier gases, and after that it will be generating the vapor. Okay, so this vapor will be flowing through this, and it will be coming to the silicon surface. Okay, so this is how the deposition of dopant will be taking place. Okay, so here basically what is going to happen, liquid source is there. Okay, this liquid source will be flowed with the carrier gases. Okay, and this carrier gas will flow through this. This will be, you can say, bubbling. It will bubble, this liquid bubbled, and this, after bubbling, it will generate a vapor. So this vapor will be flowing through the furnace, or we can say the tube in which the silicon is placed. So this vapor that is having dopant atom will flow to this surface, and it will be deposited on this surface. So this, the liquid source being used for okay. So here, in case of what is the advantage of this source with respect to solid source, if we call it here, the concentration that we are going to deposit the dopant concentration is basically, in this case, is independent of the gas flow. So whatever the gas flow is there, what is the rate of that will be independent of the dopant atom concentration. Okay, so dopant concentration will be, or the dopant concentration deposited will independent of gas flow. Okay, so gas flow rate you can call it. Okay, so whatever is there, that will not be affecting the concentration of dopant that will be deposited silicon surface. Okay, and this is considered as convenient and easy. Okay, so here, so it is considered as convenient and easy because we are not going to use the boat to place dopant. Here, the dopant is placed in a liquid form, and only the gases will be flown, and whatever vapor is generated, that will be flowing back to the tube. So it is considered as convenient, and here the concentration is it is independent of the gas. The basically the dopant concentration will depend. So here the dopant concentration will basically depend on the temperature. So what temperature this complete the diffusion process is going to take place, that will be depending on the temperature, and it also be depending on uh, the type of that dopant we are using. Okay, so what type of dopant we are using, and dopant means what type of diffusion system basically where we are going to, we can call it the diffusion system. So what type of system or diffusion use, the temperature to be regulated for the dopant concentration in case of the liquid type of this. Okay, so in case of this liquid type of uh, control of the dopant concentration is basically each cases. So here they will be based on the diffusion system and the temperature that we are going to use. Temperature we can control the concentration. So dopant concentration is here, you can call it easy control dopant concentration. Okay, and also in case of liquid type of source of a dopant, uh, there is a reduced, you can say, effect of heavy metals. Heavy metals in the sense like if we are going to use the metal or we are going to use the solid source, there is a chance of contamination. But in this liquid type of source, there is less chance of heavy metal uh, contamination. So contamination will be less in case of this liquid type of uh, dopant. So liquid type of dopants are there with respect to that liquid type of uh, reactor. If we are going to use, that is the better deposition of diffugent, or we call it the dopant atoms basically. The next we will see the next we will see the third type of reactor. So in the third type, basically it is a gaseous type of reactor. Okay. So the third one is so here the source is basically the dopant is basically in terms of gaseous form. Okay, so in that case, if the dopant is in the form of gaseous uh, form, then it is more or you can say more convenient than the even the liquid type of reactor. So in case of gaseous type of source or gaseous type of reactor, basically here we are going to use the carrier gas. So carrier gas will be used in all cases, and separately we will be providing the dopant gas. So whatever the dopant gas is there, that is being provided here. Okay, and along with that the carrier gas is used. So this carrier gas will only be helping in moving this dopant gas, and so that it will be reaching to the uh, silicon surface that we are going to diffusion make sure like diffusion is going to take place on the silicon surface. Okay, so this carrier gases will be taking this dopant gas atoms to this silicon surface. Okay, and once the reaction has been taken place at this place, then whatever waste is there, that waste gases are there that will be flowing through this wall. Okay, so this will be flowing through this wall, and whatever waste gases are there, that will be you can say pulled out by using a chemical that is called chemical trap. It will be considered as the chemical trap. Okay, so here this gaseous type of source reactors are considered as more convenient than the liquid source reactors. Okay, and also in common practice, what we do is uh, we use excess amount of dopant gases. So excess amount of dopant gas is used such that whatever the doping is being performed, then there should be a proper doping, like the proper amount of concentration of dopant should be reaching to the source. So excess amount of gas is basically used, even though this amount of gas is not going to affect the doping process, like if we are going to use basically, then this excess amount of gas is, you can say, insensitive to the rate of diffusion, or we can call like we can say it is excess amount of gas is insensitive, we can call it. It is insensitive to gas flow rate. So whatever uh, gas we are going to provide, if we are going to basically we generally we provide excess amount of dopant, because if we are going to provide excess amount of gases, the system that we are going to use for the diffusion, that system is insensitive to the whatever the rate of gas flow we are providing. Okay, so even if we can provide the excess amount of dopant, it is not like it is going to deposit a large amount of atoms on the silicon surface, but generally it is provided, generally it is given to have excess amount of dopant and gases. And here the chemical trap is used. Okay, so this chemical trap is used to basically dispose the unreacted, whatever unreacted or waste gases or waste dopants are there, that will be taken out uh, by using the chemical trap. So chemical trap is going to uh, we can say dispose, we can call it dispose. It's going to dispose unreacted dopants. So basically, whatever unreacted dopants are there, that will be taken out by using this chemical trap method, or a chemical trap will be used to dispose of the unreacted dopants. Okay, why? Because there is what is the need of this chemical trap is like, in sometimes this becomes excess amount of dopant can have uh, you can say adverse effect on the doping, and it is sometimes considered as uh, high amount of high concentration that is unreacted. If it remains there, that is considered as like, that becomes highly uh, dangerous. So we should be removing the extra amount of dopant that is available to this uh, furnace, or we call it a tea. If we are providing the dopant, that is after reaction some unreacted dopants are available, then we will be uh, removing that. So these are the three different type of reactors that are there. So from the next class, we will see different type of dopants. Okay, so there are different type of dopants are there. We have seen like boron, phosphorus, arsenic. Okay, so these are the dopants are there. So what type of this boron dopant, either liquid, gas, or solid? So what type of this boron uh, dopant is suitable for diffusion? So either liquid or solid or gas. Okay, whatever diffusion will be used, we will be checking this out into the next class. Okay, so till now, if anyone is having any doubt, you can ask. Otherwise, we will be closing.